Welcome back to day 3. I am Lynne Coe-Leavitt. I'll be the moderator for this morning's session. I'm a research department manager at the Idaho National Lab. INL, if you're not familiar with it, is one of 17 national labs of the DOE complex, and our focus is delivering science-based solutions to renewable and nuclear energy, environmental, and national security challenges. So yesterday, we had a couple different presentations. One was on AI and recycling. The other was the future of recycling technology and trends and innovations in waste conversions. This morning, our panel will talk on advanced recycling. I'm going to go ahead and introduce the panelists, and then they will get up here and spend about 30 minutes talking to you, and then we'll do questions afterwards. So first, we have Lennart Bendfeldt. Next is Neal Yancey, and third is Mark Neitzey, and I guess I should say where they're from. So Lennart is from Solutions, he's a solutions manager at eFactors. Neal Yancey is a principal engineer at the Idaho National Laboratory, and Mark Neitzey is director of sales with Van Dyke Recycling Solutions. And we will start with Lennart.
All right, good morning. My name is Lennart Bendfeldt. As was mentioned, my title is Solutions Manager, which is kind of a fancy way of saying that I take care of whatever problem, kind of comes up. So it's an all-encompassing jack-of-all-trades type of role. And what I want to talk about today was, recycling the unrecyclable. We, as eFactor 3, have tried to make a name in the field of recycling things that traditionally have been a little bit tough to recycle, finding new solutions and bringing those to market. So why does a non-traditional stream matter? Well, there's a lot of plastic and a lot of waste in those non-traditional streams. Things like agricultural films, carpet, artificial turf. These account for millions of pounds of plastic that are traditionally landfilled, or even in some cases like agricultural films, they're burned in the field, which, as we can all imagine, is number one, a big waste of plastic, but also not wonderful for the atmosphere or the environment at large. Here's just a little bit of statistics as to those streams that we just talked about. Carpet makes up 4 billion pounds annually, right? Less than 10% of that is recycled. Now, a big part of that is because it's simply difficult to recycle, and a lot of people don't have those solutions. Artificial turf, well over 200,000 pounds per field. Agricultural film, as I mentioned, over 1 billion pounds in North America. Well under 20% of that gets recycled. And as I mentioned a little bit, this is luckily being phased out, but a lot of this stuff gets burned in the field. They collect the stuff up, they put it on the field, and they burn it. And what drives the ability to recycle these things? EPR programs, landfill bans. We've seen this in California. California has mandated that certain percentages of organic materials are taken out of the stream before it goes into a landfill. And that's allowed us to go in and help our clients recycle more of their streams, even going into landfills, not just traditional recycled streams. What generally makes these non-traditional materials so difficult, right? One thing is multiple layers, right? It's very easy to recycle a pure polypropylene, polyethylene stream, but when you have things like carpet or multi-layer plastics like you might see in a yogurt cup, that gets a little bit more difficult, because how are you going to separate those materials and then process them all individually? And each different yogurt cup or each different carpet might need a different processing technology. Turf, agricultural film is difficult because it's thin and it's been sitting in the sun for 6 months. UV degrades it. It kind of can fall apart just like feathers. Not only that, it weighs pretty much feathers when it's dry, so it's difficult to transport. So all in all of these different material streams require specialized size reduction, separation, washing, drying technologies. And now, where do we see most people go wrong, right? E-Factor 3 has been around for 20 years, and in those 20 years, we've worked a lot with companies trying to attack these non-traditional streams. What makes them so difficult? Number one is, the most important, I think, is underestimating just how dirty these things are and how difficult they are for the machinery, right? Let's take agricultural films, for example. Agricultural films can be 50% dirt, right? Just grit, sand, corpses of dead animals. Anything that you would find in a field on a farm, you can find in these streams of material. And what that means is it's really tough on any machine that you run it through, right? A shredder, a screen will quickly degrade or wear down and need constant preventative maintenance. And we see people constantly underestimating those needs. That kind of ties a little bit into those operating costs. Clients will see a low price tag on a line from a different vendor, and yes, that line might be able to get them started, but what they don't see is the high cost of then keeping that operating because of the difficulty of the material. So what does successful recycling require? We need to be a little bit more thorough and a little bit more pointed as to how we operate the different steps of the recycling. So the first thing is liberating and cleaning that material. But we need that right process order. We can't just add more machines willy-nilly. We need to make sure that the machines actually have a purpose and are robust enough to process these materials. As this slide says, we need to build these systems around material reality, not assumptions, right? People will see, oh, well, if I pelletize agricultural film, I can get 5 cents a pound for the pelletized material, and then that is the number that they use to pitch to their investors, that they use to build their system. But again, they haven't really taken the reality of the material into their models. They have not assumed the fact that they're going to have twice as much downtime as a traditional recycling line because of the wear on those machines. And this is something that we as E-Factor 3 provide, is these complete processing lines for non-traditional materials, right? We start with a size reduction that is very coarse. If you put a fine shredder into an agricultural film processing operation, you're going to be changing your knives, every day almost, it seems. But we do a very coarse grind or very coarse shred. Liberate and dry clean that material, screen it, wind sift it to get out the heavy materials. And all of these different steps, it's a little tough to go into each one in detail right now, but each of these has, in our last 15 years of experience, proven to be an essential step of the puzzle. How can E-Factor 3 help? Well, exactly that experience. We have seen these projects from beginning to operation, and we've seen the missteps that people have made in these non-traditional waste streams. As I mentioned, the M&J pre-shredder, primarily a pre-shredder, but they also produce fine shredders. What's important here, again, is the coarseness of the shred and the robustness of the machine, right? The pre-shredders do not do a shear cut, right? They're not like a traditional fine shredder. They simply pull the material apart. That's important so that we have that initial step of separating the material and liberating it. If you have layers of plastic stacked on top of each other with dirt trapped in the middle, well, you need a way to get that dirt out in the first place. This is our newest partner, Broadview Group International. They produce a piece of machinery called the Rotary Impact Separator, right? So this is a form of dry cleaning, but instead of relying on friction, it's essentially a modified impact separator, right? Kind of like a hammer mill turned on its side. And the reason that this is so effective for agricultural films is, again, we're not relying on that friction, right? That's a misstep that we've seen a lot of manufacturers make. They use a traditional wash line that they would use in, bottle recycling, and they try to use it for agricultural films. And both the manufacturers and our clients have not taken into account, again, how different this non-traditional stream is, right? That dirt contamination, it'll settle in the bottom of their tanks, and then they have to stop, and one poor schmuck has to, literally dig dirt out of the bottom of a tank. But the Broadview Group International Rise is different in that it uses pure dry cleaning. We can get to about 1% ash content and 0% humidity in one pass. This is another one of our partners, EcoStar, and what is important about this step in the process is the screening technology, right? So if you've liberated the material, you put it through the pre-shredder, you now have, separated piece of plastic with a bunch of dirt on it. Well, you don't want to take all that dirt downstream, so you can shake a lot of that loose stuff off before you ever go into your cleaning process. So we pre-shred. I guess I put these slides a little out of order, but we pre-shred, then we screen, and then we would go into some kind of dry cleaning process. Now, if the client needs cleaner material, we can go into a wet washing process, but it's critical that we take these steps beforehand. This is another technology that we have been working with for a long time and that we recommend for these kinds of applications, which is the wind sifter, right? Density separation of materials. As I said, in agricultural film streams, you get anything you'll find on a farm, right? You'll find crowbars and root balls and rocks, all kinds of crap. Well, with a wind sifter, you get out that heavy stuff, right? So each step in this process, as I mentioned, has a very specific reason, and we've come to those conclusions over years and years of testing. So the wind sifter is what's going to take out all those really damaging, heavy pieces of material. I don't know if either of them are still here at the moment, but one of our main partners, Steinert, Tim Berry and Scott Chase were here yesterday. They produce magnets and eddy currents, which is of course essential in really any recycling business because a fine shredder, I think anyone here that's operated a fine shredder knows what happens when you put metal inside of one. Boom. And that's never a fun day, especially for your maintenance crew. But it's also, on the accounting side, costly, right? So especially in an agricultural film application, for example, we need some kind of magnetic separation so that we can get out, like I said, these pieces of contamination that you're going to find on a farm in agricultural film. What happens when we need to go so clean that we want to go back into blown film or something? Well, then we can go into a wet washing process, right? Friction washers, sink float tanks, etc. These can help us get down to almost 0% contamination so that we can go into delicate injection molding processes, blown film, etc. This is just kind of A to Z how we would set something like this up. Again, we're pre-shredding, right? This is not a fine shredder where you're doing a shear cut. This is just pulling the material apart, right? And then we're going to pull out the metal so that that does not affect our downstream equipment. We're going to screen that material so that any loose stuff already gets out, right? We don't have to, if we don't have to put more dirt through a washing system, we don't want to do that. So we take out any loose dirt that we can. Then the Wisteria wind sifter, as I talked about, is going to take out any of those heavy things that might have been too big to go through the screen, but nonetheless we don't want in the downstream equipment. The Rise impact separator can now get us down to 1% ash content and 0% humidity or so. As I mentioned, when we're going into delicate end products, we might want to wet wash that material then. And then, last but not least, extrusion and compounding. Yeah, that's pretty much it. Thanks, everyone.
Next, we have Neal Yancey from Idaho National Laboratory.
All right, excuse me. I'm Neal Yancey, Operations Manager for a user facility there in Idaho Falls at the Idaho National Laboratory. It's great to be a part of this panel, and Lennart did a great job of explaining the process he's going through, and I'm going to utilize what he's said already to talk about why we do some of the work we're doing for the same kind of reasons. I'll just give you a little bit of background. We started about 20 years ago in the biomass arena and processing primarily corn stover from the Midwest and making fuel. So we're funded by the Department of Energy primarily. So we're more of an energy research laboratory. Just a little bit of information. Our lab, people think, oh, you have a little small laboratory. The INL is bigger than the state of Rhode Island. So we're actually a big area-wise facility because primarily what we do is nuclear research, and we take that research out in the middle of nowhere, and we own, or the government owns all the area around it. So we're actually a very large landmass of a research facility. A small part of that is the bioenergy program that we're a part of. Back to that, so start out in corn stover. Back then, the concept was take the corn stover, make it into a pellet, it'll transport to wherever we need it to, and we'll make ethanol from that. That was originally the direction we were going. Since that time, we moved more into electric vehicles than gas cars, so we kind of gone away from the ethanol, but we still process corn stover, but we do a lot more than that now, and moved into MSW and e-waste and different things like that because of the knowledge we gained in processing materials. Again, we're a research facility. We work with industry to help them overcome some of the challenges that they're facing, help de-risk and take care of some of that processing stress away from them as they're building new processes. Back in about 2013, 2014, we moved into the facility where we're at now and got the designation as a national user facility. So prior to that, a process demonstration unit, all of our system was built in cargo containers, and we could ship it around the country. That was kind of our thought, was we were going to go around and demonstrate all around the country. We never really did much of that. We stayed pretty much there in Idaho Falls area. And in fact, then moved inside this facility we have now and set up our system there, and it's more permanent. We still have the ability to loan out equipment and go test other places, but we really primarily operate out of the Idaho Falls area. Like I said, we started out with doing corn stover and wood waste. Making ethanol was our early on process. Now we process a variety of different materials. Whatever our industry partners come to us and say, hey, we need help with how do we process this material. So we've done windmill blades, municipal waste, circuit boards, in addition to the traditional corn stover and other materials that we started out with. When we started out doing the corn stover, the concept was let's do it in as few steps as we can to get the product into a pellet and get it out and move it downstream. Just like what Lennart was talking about, you can't, some of those steps are important. You can't eliminate a step and think that you're going to be successful downstream. And so early on, the industry really pushed to say, we're going to grind these bales in a single step. Well, you talked about how much dirt and stuff comes in with the waste you got. The same thing is true of a corn stover bale. We get a corn stover bale in it, maybe 30% dirt, and we might have a hammer or a crowbar in there as well. And if we try to grind that all up in one step, we're going to damage our equipment, and we're just going to send that material downstream. So we learned early on, it's important for us to break that bale apart, get the dirt out, get the rocks out, the contaminants out, and then start processing it in a way that's going to give a better final product to the end user. We've taken that concept to all of our different materials. So back in about 2020 and 2021, we had an expansion. We realized that process of how important it was to have these different components in our system to be able to screen out contaminants, grind specifically to what our customer or our partner was needing, and then make it into a final product again, our primary goal along the way has always been energy. Now, we work with industry partners. That may not be the case at all. We've worked with companies like Kimberly-Clark making toilet paper, R.J. Reynolds making paper for the tobacco. So we've done a lot of other things besides energy, but that's what our main focus is from our funding from the Department of Energy. But we started building this facility up and expanding it, really looking at how do we take that material in, how do we get it broken into, or fed into our system so that we can pull out contaminants, what type of screens, what type of grinders do we use, and so we started building a different system than what we started with when we were just primarily working at corn stover. So again, looking at material introduction, we partnered with a company right now, Warren & Berg out of California, where we originally were doing this baled corn stover, now where we want to handle MSW, and it's a whole different process. And so they've been working with us to develop a debaling system, so we get in the baled MRF residuals, for instance, and want to break those apart. We have a lot of trouble with those, the film plastics wrapping around our mills. So how do we break that bale apart, pull out the film plastics at the same time, get that material flowing to where there's still a lot of rocks and grit and glass in there that we want to pull out and start sorting that. So material introduction, I call it, is the important first step of that. How do we take that material and get it flowing into our system where we can start working with it? Then we've got a series of different types of grinders that we work with. Some of the folks here at the expo, Vecoplan is one of the shredders we have. Forest Concepts is a system we have. We work with ball mills and with the circuit boards. Hammer mills was our old go-to for from the beginning. Knife mills and different. So depending on what our customer comes to us with and says this is the material we want, we're going to use a different type of mill for that process. Or if we are working with a MRF residual like we are in this case, we're going to try to separate the plastics from the paper and cardboard, and each of those may go through a different milling process. Separation and sorting is a big part of what we do, and same with what Lennart was mentioning there is we got to get the dirt out. So in this case, and Statler's here, we actually have one of their ballistic screens here. So let's say we're dealing with MRF residuals. We're going to bring that material into the ballistic screen fairly early on. It's going to separate out our two-dimensional, three-dimensional materials, drop out 2-inch minus out the bottom, and each one of those streams we're going to process differently. So, but screening and separation is a big part of what we do. Even if we get down, as we get down to maybe we've isolated plastics, there's different densities of plastics, and we'll size those to a certain size fraction. We can separate that based on density. So again, just depending on what the customers are after, we're going to tailor that process and help scale that up. We aren't a production facility, but we can produce material up to 5 to even 10 tons per hour for some processes. We typically, a lot of our testing we do is done on daily small batch operations, but we have tests that have run for 6 months, 24 hours a day. So we can tailor our process to what a customer needs. And again, we're a user facility. We can operate a number of different ways. We have grants and funds that we can help work with you directly on, but when we do things like that, that's usually we want that publicly disseminated information. We also can work off of a private contract with an individual as well, and so we do all of that. Anywhere from public information that gets put out and we fund it completely to completely funded by our partner, and the data is completely proprietary. So any of those processes in between there is what we can do. Again, going back to the screen, like I said, we bring in in one case we were working with a tribe, local Native American tribe close by us, the Shoban tribe, and we were working with black bag garbage directly from residential waste. They wanted to look at what can we, they didn't do any type of recycling at their facility, and we were working with them to help them identify what they could do. So we took in black bag garbage, ran it across the ballistic screen, got the 3D material and the 2D material separated out and the fines, and then started looking at how do we handle each of those different materials. We took the 2-inch minus material, ran it across the disc screen, got some more of the contaminants, the grit and stuff removed out, and took the remaining material and went through a size reduction process and a density separation. So we were then able to get our high density plastics in one fraction, and this is just with a single step depending on what our customer might want. We may go through multiple steps, but we got the high density plastics separated from the mixed paper, cardboard, and styrofoams. We could then take that again and split that again and go down even further and separate that material. We were able to do that in just a couple steps. So we're debaling, running across the Stadler, going across the disc screen, pulling out the materials, size reduction, density separation, came out with a very hard or a high concentration of high density plastics, and we're then extruding that into a filament that we could 3D print with. More of a demonstration type thing than production, but it showed what we could do with just black bag garbage. Again, so we took the other two fractions, the 2D and 3-dimensional material, and went through sorting processes with it as well. So air separation is one of the things that we were demonstrating in this case. Took that material, dropped out the heavy materials, again, kind of similar to what you were doing, drop out the contaminants, the metal, the dirt, the rocks that might have been in that material, and then concentrated the higher density plastics and aluminum cans, different things from that waste. You mentioned eddy current separation and magnetics as well. That's part of what we have to offer within our system as well. So let's say we're taking that material from that from the Stadler ballistic screen. We're taking that 3-dimensional material. It's got a lot of aluminum cans in it. We're going to run it across the eddy current separator. We're going to pull out that aluminum cans. That eddy current separator is going to pay for itself pretty quick in just separation and collection of aluminum cans. But it also does well at getting out other things like copper wire and different things that we don't want in our downstream processes. It's going to affect our mills. We don't want that kind of metal contamination going into our plastic streams. So we can separate the ferrous out with magnets, of course, and the eddy current non-ferrous metals, and then a rock trap just to remove any of the other heavier density like rocks, grit, and glass. Densification is another capability we have. We have bench scale pellet mills all the way up to 5 tons per hour systems. So most of our pellet mills are Bliss, but we work with others as well. So we can take that material, create something that's very low density. You talk about the feather type stuff that very hard to transport. We can take that and densify that. Now we've got a product that's much higher density, and we can transport that or feed it into a process, whatever the case may be. Also operate a cuber, so we can make the 1-inch by 1-inch cubes, or we can put a round die on there as well, make a called cube, but it's a cylinder cube. Or we can briquette, or we can extrude material like I mentioned earlier. So down at the bottom right for you guys is an extrusion process that we're showing, where we took just the final product where we had isolated all the plastics, and we're extruding that into a filament that we could 3D print material from. Another capability that we have in-house, so we have, within our group, we've got technicians, laborers, all the way up to equipment operators, and then to our researchers, PhD, engineers and scientists that we work with. A couple of the capabilities we have is in software and in electrical engineering, and so we've developed digital models of all the equipment within our process. So we can work with the client, understand what they're processing. We can model that material before we ever go into the lab and actually run that material. So the models are only as good as the data you put in. So if it's a completely new process, we may need to generate some data before that model is really going to be really effective. But once we have that data, if you come in with a material type, or if you come in with a new process, we can model that for you and help you understand at least a better idea of how that material is going to perform before we even put it in the machine. Helps us to reduce the number of in the field testing that we have to do, because we can at least narrow down how we want to operate our tests. But we've done this for almost all the equipment within our facility. Data management is very important as well. Every motor in our process we're collecting data from, so it gets connected to a network, to a computer system where we're collecting that data, and we've done that from when we first opened the facility and back in 2010. So I can go back and say, okay, I want to look at all the times we've run corn stover, and I want to run corn stover at 10% moisture, and with this grinder, how did it perform? So we can pull all that data, and that's publicly available data. We can share that with any of you. How is that going to perform for your material? So if we've run a material like what you've done before, and we've run numerous kinds of woods, herbaceous materials getting into the MSW garbage and plastic and things, all that data we've recorded and kept for customers in the future. And how do we use that data? Here's an example of how we use that data. So early on, when we purchased the system we have now, back in 2010, we were operating corn stover. Our manufacturer gave us a nameplate production rate that we should hit. It was supposed to operate at 5 tons per hour, and we couldn't hit it, especially if you get a little bit of moisture in there. We couldn't hit that nameplate production rate, and we're like, what's going on here? We're feeding the system, we're trying to run at 5 tons per hour, and we're just not hitting it. The feed tables, we got it set. It's feeding in what we think, but it's kicking back, it's pushing back all the time. So we start looking at that data, and we realize this was a high-speed mill running corn stover into it. The way the bale of corn stover is made is it's made in sections, or wafers, or leaves, as you call it. So it also comes apart in that same manner. So it tends to not just pull apart evenly. You get these wafers that come off at sections from the debaling system, and that bunches of material that come off in the process create uneven flow that affects us downstream. And so we say we need to operate at 5 tons per hour in this. Let's see if we got this red line here kind of represents what 5 tons per hour is. But you can see most of the time we're not operating at that at all, and then sometimes we're double that. So the system's seeing spikes of 10 or 15 tons per hour, which is overloading, and then it's shutting down, and then we operate for 2 or 3 minutes where we're not getting 1 ton per hour because it's not even flowing. So we're really, the biggest problem with what we're experiencing here is not that we can't do 5 tons per hour, it's that we're not feeding our system uniformly. And if you look at the bottom left, we overlaid 3 different things here. So we've got the current from our bale grinder, and it's going up and down. The spike in this material as it bunches off. We've got the current from the hammer mill. We overlaid over the top of it. The matches perfectly. And then we've also got sensors that look at the depth of the material in the conveyors feeding the systems. And we realize this is all a problem of uneven flow. It's not that our hammer mill can't do 5 tons per hour. It's that we're feeding at spikes of 15 tons per hour and then nothing, and then 20 tons per hour and then nothing. And so we're stalling out our hammer mill because we're not feeding it uniformly. So then we went to a different type of feed system over here on the right, and got to have a more consistent feed. Because we got a more consistent feed, we could get our production rate up to where the capacity of the system needed to be. Again, my point there is just that we were able to take data from our system and begin to understand why it was not performing the way we want it to. And that's what we use all that kind of data for, is how do we see, why did moisture affect something? Why did a different screen affect things a different way? And so that's kind of a big part of what we produce is not the material that comes out, but the data that comes out of those runs. That's just as important as the actual material itself. So just wanted to give a shout out to our team. Again, we've got a team from technicians and laborers all the way up to researchers. Got a good group of people that we work with. Recently had a ribbon cutting where the Secretary of Energy came out and visited our facility. Work with a lot of industry partners, really have a great team. Bring in interns from all the way from high school on up to college to get them indoctrinated and prepared to work in the real world with this. Really have a great facility. And as I mentioned, one of the things that we do is work with industry partners to develop new things. So example was that the debaling process with Warren and Berg is one of the systems that we worked with our industry partners to develop new pieces of equipment. We just brought in a new torrefaction system, so we work with thermally treating materials to help us in size reduction and preparing that material for downstream separations. So we work and partner with a company with torrefying material. I haven't mentioned drying, but we also have a rotary dryer within our system. So again, drying, screening, size reduction is all part of what we work with here. We also have our own fabrication shop, so if there are parts and pieces that we need to build, we can build those in-house if we need to do that. What does that mean for industry? I mean, the whole idea of this is we're a national lab with a facility that is designed to be a user facility for industry. We want industry partners to come and utilize our facility rather than try to build something themselves. Let us take on that risk. This is built from tax dollars from you guys, thank you. Let us help you scale your processes up to where you can go back to your investing partners and say, look, we've tested it here at the National Lab. We're ready to move to that next step and go into the field. Don't make that step with that, make that jump from laboratory to the field without doing some pilot scale research. And that's what we're here to do, is help de-risk that for you guys and get you the results you need so you're more confident in the data you're producing. Pilot scale testing is a big part of what we do. We also do very detailed laboratory research as well, where we have, again, funding from the national labs all the way up to just partnerships with industry is where we get our funding from. That's it. I'll stop there and we can have questions later. Thank you.
Next, we have Mark Neitzey from Van Dyke Recycling Solutions.
Good morning, everyone. Thanks for coming out for presentations this morning. I'm going to talk, this was a panel about innovations to recover more. I was added to the panel late. Our company primarily is in the MRF space, so that's what we're going to focus on today. Developments in sorting film and flexible packaging from a MRF. So my agenda is just to explain who I am, who is Van Dyke, talk through some recent projects that Van Dyke has done, give you a little history on MRF film as we see it, and then talk about preparation is the key. I've given preparation is the key talk before, but I think it's still relevant to the MRF space for sure. Then talk specifically about clean MRF film that is being made today, and then open it up for a Q&A. So my name is Mark Neitzey. I've now worked at Van Dyke for 25 years, the last 14 or 12 to 14, because I took a little hiatus as the sales director for Van Dyke. A graduate of Texas A&M, is where my wife also went, and that's where my 3 kids attended as well. I base myself in Houston, but I'm on the road every week. I'm on the road every week seeing a different facility around the country, and I've really kind of seen MRFs evolve and change over the years, and hopefully I can that will show in today's presentation. All right, there we go. Who is Van Dyke? Van Dyke is headquartered in Norwalk, Connecticut. We have been in business since 1984, providing best-in-class MRF equipment. I didn't do it. Do you need to get that? We do turnkey design, supply, installation, and service support, primarily in residential recycling systems or MRFs, material recovery facilities. Since 1984, we've done over 2,400 projects. We have equipment in 250 single-stream MRFs. You know, the number of MRFs is shrinking due to consolidation. So we have a broad range of experience. That doesn't mean we've done 250 turnkey MRFs, but we might have supplied a baler at one, or done a retrofit, or added an optical at one, and that just gains us experience and knowledge. And you know, lessons learned for the next one, for the next one, for the next one. We have installed over 1,100 optical sorters since 2003, and that points to that experience and that expertise because you learn from each project, and these systems are getting bigger and more sophisticated as the years go on. We have world-class equipment partners, and we back that up with service support, and I'll talk a little bit more about that. Neal's talking about his lab, we do have a test center in Norwalk, Connecticut that is for everyone in this room's use. Whether you're a brand owner or maybe you are a MRF operator, if you have something that is questionable, can it be recycled? Can it be seen by the technology that's out there today? We don't just have an optical on a loop, we have a full-blown test center with screens, ballistic separator, multiple scenarios or situations for setting up for an optical sorter. Also at Norwalk is our large parts distribution warehouse where we have $35 million in spare parts. That is needed to support today's MRF. Today's MRF runs 24 hours a day, 2 and 3 shift operation. The material will not stop coming in, and downtime is super critical to these plants, so this is a big facility based in Norwalk, so you can easily access parts to it. We also have a factory rebuild shop there as well, and that factory rebuild shop is where we bring in maintenance and operations teams from around the country for training. So we have Van Dyke University that offers training for balers, for optical sorters, and for control systems. That's a picture of our service team. We have 50 employees that are factory-trained service techs based all over North America. They support the equipment that we've installed. 2 of our equipment partners, Tomra and Palank, those are ranked #1 and #2 in the world as far as sensor-based optical sorters, so we're proud to be partnered with both of those companies. A recent addition for us is Gray Parrot AI analyzers, which allows you to place an analyzer in different places of a MRF and collect data, and that data could be used to learn about input composition, learn about what's being lost in the end-of-line residue, also track your quality of all the products that you're making and share that with your customers. So we are just on the front of this, but we are having really good feedback from where we have installed the Gray Parrots for the amount of data that you are able to see and then in real time make changes to your system to make sure it's optimized to its maximum performance. I'll breeze through these, but these are recent projects that Van Dyke has done turnkey. We did a large plastics facility for Freepoint in Ohio. It's a mixture of rigid and film plastics that's ultimately being made into pyrolysis. We did the single stream system in Connecticut. That's the middle slide. That's where the Gray Parrot, we have 15 Gray Parrot analyzers. That's where all the data is coming from in real time for a MRF. The picture on the far right is the Waste Connections Groot Plainfield facility in Chicago. They don't publicize this a lot, but this is the most automated MRF in North America today. They're doing 40 tons an hour with only 4 people in the plant. So it's a pretty impressive plant to see if you'd want a tour. This is basically our ops team spent most of 2025 installing these systems. We did 2 large 40-ton-an-hour systems in Texas for WM. We did a large film processing plant in Indiana for Nova. We did 3 large EPR plants in Canada for the CMO of Canada, 2 with WM and 1 with GFL. And we've just finished up commissioning the Indianapolis plant for WM. It's got some innovative film stuff that we'll talk about in a second. All right, we're going to shift gears, talk about the history. I know this might bore people to death, but the history of MRF film. For those that don't know, single stream recycling, collection, and then single stream processing really was born in the late 1990s, early 2000s. So we're only 25, 26 years into single stream processing as we know it today. In 2005, so very early on, you started to see pre-sort, so that would be the conveyor, the inbound material would see first. You started to see film suction systems added to pre-sort. So here you see 2 guys grabbing film, flexible packaging, bags, and they're holding them up and they're being sucked up in a tube and then transported via the pipes to a material separator, drop down into a bunker. So this was started to see this trend in 2005. So in about 2 or 3 years' time, most of the MRFs that you would visit would have some sort of film suction system on the front end. However, shortly after that, it was determined that, and I'm not going to read all of that, but film, primarily grocery store bags, Walmart bags, Target bags, were a nuisance. And yes, you were supposed to try to pick those out on the front end or at the pre-sort. But if you do a calculation on the number of bags in these systems, you would have needed 32 human sorters to sort the film properly, and that's the only grade they would be sorting, and it was a limited market. So you saw those film systems start to be turned off because there was not a market for that film. It was somewhat dirty. There was some human error. There was, whatever. Still materials in some of those film bags. So it was, you would go and see these elaborate tubes throughout these systems, but most of them were turned off. This is what happened when you didn't grab the film on the pre-sort. You had a crazy amount of wrapping on the star screens. And I know this conference and others have talked about this for years and years, but this was a real problem for the MRF technology in the early years leading up to future developments, because you still needed to run at a very high capacity, and you still needed to have some separation devices, but the amount of film that was being put into the stream really made it challenging for the star screen equipment. So around 2014, there was a development of non-wrapping star screens. The year my company put our first non-wrapping screens in was 2014. We did it at City Karting in Connecticut, and we did it at Recology, Pier 96. It was a game changer for our company and a little bit to the industry as well. In essence, it wasn't rocket science. The shafts on the star screen were just made to have a larger diameter to where the film bags would not wrap around the screen. That allowed for, you didn't have to clean every hour, you didn't have to clean every shift, you didn't have to clean at break. The screen still maintained its screening performance, so it was, and the screens also got wider around the same time. So it allowed for, you started to see plants go to 30 tons an hour, 35 tons an hour, 40, 50 tons an hour. So these are large facilities that need high capacity separation. Around 2015 is when you started to see the ballistic separators be placed into MRFs. My company calls this device an elliptical, similar to the elliptical that you see here on the far right. It's the one I didn't work out on this morning, but in essence, it's a paddle system where it walks two-dimensional light material up the ballistic and three-dimensional rigid material bounces back. And then the picture in the middle shows it allows for fines to fall through. So early on, there were mistakes made by my company and others about placement of this screen, and it was used incorrectly as a paper container separation device. I think that has been corrected in our industry. That's not the norm now. However, if placed properly, and that placement is right before the container line at a MRF, so right before the bottle and can line at a MRF, that is the nicest, coolest piece of equipment in the entire plant. It handles the 3 F's, as I call them: film, light sheet fiber, like single sheet light floating fiber, and fines. So film and light sheet fiber walk over the ballistic, fines fall through, and then the bottle and can line is perfectly prepared to set up the opticals to work. This is important because in a modern day, fully automated MRF, you're using optical sorting to make a sorting decision, really to try to recover all the cardboard, all the whatever you would call it, writing papers, mixed paper, newspaper, and leave what's left. Well, what's left at that point is bottles, cans, and film. So we have channeled the bottles, cans, and film to this ballistic separator, and now we've walked the film over this ballistic separator, so you have a high concentration of film. That is how we're able to recover more film. We just now have to clean it to where it can be a sellable commodity. So a couple other slides about the history. 2013, we supplied equipment to the Sims group in Brooklyn, New York. This plant is still running today. It's owned and operated by Circular Services. It's hard to believe this plant's now 13 years old. I recommend anybody that hasn't seen it to go see it. It's really kind of a cool facility. It's not single stream though. It is bottles, cans, metals, glass, all in a unique stream in New York City, all delivered in bags. But we learned lessons here because it has ballistic separators, it separates by size, and it uses optical sorting to make a film grade. So lessons learned from this plant definitely have been applied over the last 12, 13 years. In 2018, we were fortunate enough to be awarded the retrofit project for J.P. Mascaro, which was the flexible film project together with RRS, I think was the consultant. This took an existing MRF facility and added optical sorting to try to recover flexible packaging and film. This from single stream. Now keep in mind this previous slide, Sims is a dual stream plant. This was a challenging installation, challenging project. It obviously got installed during COVID. That also made it somewhat challenging, but lessons learned from this are also paying dividends for us, that experience that we got from this going forward. Last slide about history, you started to see more same type of pipes, same types of air transport system for film, but now bolted on the separation housing of an optical sorter. So for those of you who haven't seen it, but an optical sorter has a high-speed belt. It has the sensor hovering over the belt, recognizing the material, and then an air bar makes a sorting decision to eject what you want it to eject, and then pass through what you want it to pass through. You started to see multiple grades of material be ejected, and then one of these hoods would suck up, like let's say you were ejecting all polyethylene, So that means the LD and the HD would be combined. You could then suck up the light film from the HD. It worked a little bit, wasn't perfect, but it was a start. Again, it was a learning process. So I'm looking out there, and I see most of you guys are on your phones and you're bored to tears. So we're going to shift gears for a little bit, and we're going to talk about sex for just a moment. Optical sorters are sexy. They are super sexy. The room would be filled if we were talking about robots and optical sorters. The room would be standing room only if we were talking about AI. The four of us are jealous we weren't on the AI panel, right? Because that is a sexy topic to talk about. Preparing the material, how we've all kind of talked about, not very sexy. But that's what I wanted to show you. There's AI. For some of you guys that don't know that in the room. Can these intelligent separation devices help MRFs? The answer is yes, but you have to, that got turned around, prepare the material properly for the technology. You cannot just drop in a piece of equipment to solve your problems. You can't really just add AI to monitor the material to get the data unless you can prepare it properly and feed it at a single layer. So there's been several advancements that, for several things, kind of led us to these more automated MRFs, led us to more intelligent separation, and led us to what we're talking about today is film recovery. This is what our MRFs are faced with today, this type of material, right? So it's really great to talk about that AI can help with this and AI can help with that, but if you don't do the nuts and bolts of preparing the material properly, it can't see the material to recognize it. We're really doing needles in a haystack. This is an auger type screen, a spiral screen from Gunther's, a company we represent. So you're basically sizing, let me see if I can go back. You're sizing the material and preparing it using non-wrapping screening technology, getting it to single layers, and then it's a combination of conveyors at the right width, the right speeds, the right angles, the right cleats, the right sequencing, and then you get to the optical sorter speed-up belt. This belt in a modern MRF can run up to 1,200 feet per minute. You need a wind tunnel to do that. If you don't have a wind tunnel at 500 feet per minute, film and paper start to fly around and they're not stable on the belt. So you see the development of air boosters, wind tunnels that allow the belt speed of these conveyors to go at very high speeds, 1,000, 1,200 feet a minute, but the material is stabilized so the optical sorter can still do its thing and successfully sort. So this has been a big development because now you can run an optical sorter with very light material, up to 10, 12 tons an hour. Another development, I think Lennart's company represents this. This is a Wisteria disc spreader. This, in essence, is a manure spreader if you're like in the farm land. And if you've got a 10-foot wide optical sorter, but the material's falling on the belt only on 2 foot wide, you're not utilizing that belt properly. You're not getting a proper spread. So this has been a really big development in automated single stream sorting because it allows for material to be spread across the full width of a belt, 10 foot plus, to get a nice even feed. And then this is a picture of the optical setup all tricked out. There's the disc spreader. There's the wind tunnel, the aero booster. There's the high-speed conveyor, which to keep a conveyor at that speed stable over the course of a shift, it's a super heavy-duty conveyor, and then leads up to the optical. Once the optical is recognized and ejected the material, the separation housing has also improved over the last several years to be more accepting, more accurate, the mechanical separation is as important as the optical separation. Then there's been optical sorter advancements as well over the last several years. Optical sorters being sold today are future-proof. As new technologies come out, they can just be added in. The near-infrared spectrometer that has been the backbone of an optical sorter has been improved and enhanced with higher and higher resolution. You now, using near-infrared, so not using a camera, not using AI, you can see and recognize and determine the difference between linear low and low-density polyethylene. You can see and recognize and determine the difference between low melt or PET trays from PET bottles and natural from white and opaque. So the technology has continued to evolve. Black objects can be seen using a laser. Metal detection sensors are becoming more the norm. And then more recently, AI sensors are being incorporated with all of these sensors. I get asked all the time, will AI take over for all those other sensors? You know, my answer is I don't know, but there is still some, the experts at Palank, at Tomra tell me you still need a combination of sensors to make a correct sorting decision. So this picture in the lower left, I just put that up there for everyone to look at. That is 3 different materials that if you just had a camera or just using AI, it would struggle to determine. One is film plastic, one is a dirty tissue, and one is a piece of crumpled up paper. So you need a combination of sensors to see that material. Okay, we have done a few projects recently where we're given the directive of we need to make clean MRF film. Well, that's very difficult to do. Making clean film, period, is very difficult to do. Involving it in a MRF environment is extremely difficult to do. So we ask, what is the spec? The spec is that we were challenged with is less than 5% prohibitives, or basically anything that's not film or flexible packaging, less than 5%. That includes paper. I think it's the hardest thing that companies like ours do. I really do. It is super challenging. It's not easy. It's not for the faint of heart. I want everyone to think about this. You leave this conference, you go to a Target, and you buy, let's say you buy a pack of batteries. They give you a Target bag, you put the batteries in that bag and the receipt in that bag. You get to your car, you pull the batteries out to use them. What remains is the receipt and the bag. At that moment, that's 50% paper and 50% film. And we've got to get to 5% and 95% to even make it considered to be sellable. So that's extremely challenging, extremely difficult. How we are doing it, and I'm not saying this is the only way, but this is how we're doing it and able to make the spec we're looking for is, as I discussed earlier, we're using positive sorting throughout a MRF, getting all the other commodities, the fiber and the cardboard out. We're channeling the remaining fraction, heavy supply of film, to the ballistic separator, and we're making what walks over that ballistic a 2D fraction. We're then sending that to an optical sorter to positively eject on all film. So that optical sorter has the right sensors to do its thing, and those right sensors include metal sensor, laser object detection, the NIR. It has an AI sensor in it, so it's got a multitude of sensors to make a sorting decision. We've prepared the material properly, then we eject positively on anything that's film. Then we go to a second optical sorter. That second optical sorter is set up where you can either eject positively, the film again, so it's 2 times positive, or you can eject anything that's not film. So you have the option to do a negative sort or a positive sort. But that is 2 steps optically. And then the optical sorter, if you are going to use air conveyance, we are ejecting from an optical sorter straight into the hood. We're not just letting material float around and hope it gets sucked up there. Then you still need a bunker and a baler. So we're talking about a crazy high amount of capital investment needed to do this, but it is possible. We are making film that is less than 5% prohibitives, but it takes double sorting with a bunch of extra conveyors and a lot of preparation, but it is possible. So that is a picture from the Fort Worth facility that WM has. That tested at 97% film. That's the setup there. This is a 3D model of that system. So basically, where, I don't know if that, I'm not very good with this pointer, but where number 12 is where the ballistic separator is. It walks the film to where you see number 20. Those are the double optical sorters in line, prepared, and then it makes a clean film from there. These are a couple pictures from the Canadian facility that's making also film to that same specification. So in conclusion, it is possible, it's not easy, it takes a lot of capital to do, and once you have it clean, there is minimal markets to sell to. So I really appreciate your time, and take any questions, and thanks again.
Those were three really great presentations. I'd like to open it up for questions. It's either no questions because these guys did a fantastic job explaining everything, or
We're very thorough.
yeah, very thorough.